Okay, so are you ready to kind of dive deep into some really complex astrophysics?
Always ready.
Yeah. I mean,
Ugh.
I feel like this is what people want, right? They want to try to understand dark matter,
Absolutely.
dark energy.
These are,
What is all this stuff?
yeah, these are the biggest mysteries in the cosmos.
Right.
So,
So we've got some excerpts from this text you sent over. It's called Dark Matter Energy for Podcast.txt.
okay.
And we're going to try to unpack some of this stuff.
All right, let's do it.
And hopefully everybody listening comes away with a little bit more of an understanding of these really, really complex concepts.
Yeah, and I think this deep dive will definitely offer a fresh perspective on the universe as we know it.
So to get started, I mean, I think a lot of people have at least heard of Einstein's theory of general relativity.
Yeah.
But just to kind of quickly summarize it, the main idea is that energy and space-time are actually intertwined,
Right.
right? It's not like this kind of static background stage where everything just happens.
Yeah.
It's like they're woven together, they affect each other.
Yeah. It's this kind of like, it's like a cosmic dance, right?
I love that analogy.
Where energy warps space-time, and then that warp kind of guides how energy moves.
And that's gravity.
Exactly. It revolutionized the way we think about gravity.
And it's amazing, right? Like this one idea can explain so much.
It's so elegant.
It's so beautiful.
Yeah.
And it actually leads us to these three different types of energy, right?
That's right.
We've got the normal matter, like the stuff that we're made of, the planets, the stars.
Yep. The stuff we can see and touch.
Exactly.
The familiar stuff.
And then we have this mysterious dark matter and dark energy.
The unknowns.
Right. So why dark? Why do we call them dark?
Well, it basically signifies the mystery surrounding them.
Okay.
We can't see them directly.
Yeah.
And their nature, like what they're actually made of, still remains largely unknown.
We know that they're there because we can kind of see their effects,
Exactly.
but we don't know what they are.
Yeah, their gravitational influence on the visible matter, on the stuff we can see,
Right.
and on how the universe expands. That's how we know they're there.
It's like they're leaving these fingerprints,
Yes,
but we haven't actually caught them in the act.
precisely.
And to make it even more complicated, we have the standard model of physics, which describes normal matter pretty well.
Right.
But we lack such a model for dark matter and dark energy.
Exactly. And that's part of the challenge.
Just a huge puzzle.
It is.
Okay, so now we're getting to the really, really interesting part of all of this.
Okay.
This text that we're looking at. It introduces this brand new idea, and it's called changing space.
Intriguing, isn't it?
Yeah.
Changing space.
Or CSpace.
CSpace, yeah.
So what is that?
So imagine, instead of thinking of space as this like static backdrop,
Okay.
CSpace kind of views the universe as a single dynamic entity.
The whole universe is just one thing.
In essence, yes, with properties like shape and elasticity.
So like it can stretch and bend.
Exactly. Like imagine a giant, flexible, space.
Okay, I'm starting to kind of get a picture of this.
It's definitely a mind-bending concept.
Yeah, it's a lot different than what we normally think about.
Yeah, it challenges the traditional view of separating space-time and energy, which, we've been talking about with general relativity.
So you're saying this kind of throws general relativity out the window.
Not necessarily throws it out, but more like
Okay.
reframes it, maybe builds on it in a way.
Okay, so how does this CSpace then affect how we think about dark matter and dark energy?
Well, it completely changes the game, potentially.
Okay.
Let's start with dark matter. Right now, a lot of physicists believe that dark matter is made up of these undiscovered particles.
Right, they're looking for them in these big underground experiments and stuff.
Exactly. They're searching for these weakly interacting massive particles, WIMPs.
Yeah, heard of those.
But this text, with the CSpace idea, suggests that dark matter might not be made of particles at all.
Okay, so no particles, what else could it be?
Well, according to this text, it could be explained by moving waves in CSpace.
Waves, like waves in the ocean.
Kind of, yeah, but these would be waves in the fabric of space itself.
Wow, that's a really different way of thinking about it.
Right. So instead of searching for these elusive particles, we might need to look for these waves.
So we've been looking in the wrong place this whole time.
Potentially, yeah. It's a major shift in perspective.
And that could mean that all this research that's been going on to try to find these dark matter particles has been kind
A
of...
dead end. Maybe.
Yeah.
But it's exciting because it opens up a whole new avenue of exploration.
That's true. That's true. So, okay, so we've got these waves. Instead of particles, how do they count for dark matter?
Well, the text says these waves would act sort of similarly to gravitational waves, the ripples in spacetime caused by massive objects like black holes colliding.
Yeah, those were discovered a few years ago, right?
Exactly. But these CSpace waves would have much longer wavelengths and slower speeds.
Okay, so they'd be more like gentle swells than these big crashing waves.
Yeah, good analogy.
Okay, so then those swells, they're causing the extra gravity.
Precisely. They would interact with galaxies and galaxy clusters,
Okay.
causing the extra gravitational pull that we currently attribute to dark matter.
So if CSpace is right, we might never find dark matter particles because they don't exist.
That's the implication, yeah. Pretty mind-blowing, right?
It is. Okay, so we've talked about how CSpace kind of changes our view of dark matter,
Mm-hmm.
but what about dark energy?
This is where CSpace gets even more radical, I would say.
Okay, how so?
Because it argues that dark energy might not even exist at all.
Hold on, I thought dark energy was like this fundamental force that's pushing the universe apart.
That's the prevailing theory, yes.
And it's causing the universe to expand faster and faster.
Right, that's the accelerating expansion we observe.
Yeah.
But the text proposes that our whole understanding of dark energy might stem from misinterpreting measurements of redshift.
Okay, so redshift, that's basically how the light from distant galaxies gets stretched as it travels to us.
Exactly, and the further away a galaxy is, the more its light is redshifted.
So we interpret that as the universe expanding, right?
Right, and the rate of redshift has been interpreted as accelerating.
Okay.
But the text outlines several other things that could be causing this redshift that we observe.
Okay, so what are some of these alternative explanations?
Well, for instance, the text mentions something called a fermion carrier ball.
A fermion carrier ball, what is that?
So in quantum physics, fermions are the fundamental particles that make up matter.
Okay, like electrons and quarks and stuff like that.
Right, exactly.
Okay.
So this fermion carrier ball is like this, I guess you could picture it as a tiny ball that carries these fermions.
Yeah, okay.
And the idea is that maybe the size of this ball is changing, which could affect how we measure the universe's expansion.
Okay, so that's one explanation. What else?
The second is simply the movement of galaxies and stars. It could be that the redshift measurements are being influenced by the way galaxies move in relation to each other. Some moving towards us, some moving away.
Right, so it's not just the expansion of the universe, but also the individual movements of these galaxies that could be affecting redshift.
Exactly. Then the third one, it gets a little more mind-bending, is the idea that the speed of light, which we generally consider constant, might actually be variable.
Wait, so the speed of light could change?
That's what the text proposes as a possibility. And if the speed of light was different in the early universe, that could affect how we interpret redshift measurements today.
Okay, so that's three pretty radical ideas already. Is there a fourth one?
Yes. The fourth one is that our measurements of distances in space might be more dynamic than we think. So we use things like supernovae, these exploding stars, to measure distances in the universe.
Right, because they have a known brightness, so we can kind of calculate how far away they are.
Exactly, but the text suggests that maybe there are factors that we haven't accounted for that could affect those distance measurements, making them less reliable than we assume.
So all these different factors could be contributing to the redshift that we're measuring.
Potentially, yeah. And the text really emphasizes that we need a much deeper understanding of the underlying physics before we can jump to any conclusions about dark energy.
Okay, so maybe dark energy isn't this mysterious force pushing the universe apart?
Maybe not.
Maybe it's something else entirely.
Or maybe it's a combination of factors, right? We just don't know yet.
Yeah, it's incredible to think that there's so much out there that we still don't understand.
It's humbling, but it's also exciting.
It is. So to kind of recap what we've talked about, we've got this new concept, CSpace, that could completely change the way we think about the universe.
Yes, it's a bold idea.
It could rewrite our understanding of both dark matter and dark energy.
Potentially, yeah. It challenges a lot of our assumptions.
And it opens up a whole new set of questions and areas for research.
Absolutely.
So here's one final question I'd like to leave everyone with.
Okay, hit me.
If CSpace is right, and the universe isn't actually accelerating in its expansion,
Okay.
what does that mean for the ultimate fate of the universe?
Wow, that is a big question.
It is. Does it keep expanding forever? Does it eventually collapse?
I don't know, but it definitely makes you ponder the vastness of it all.
Yeah, and the fact that we're still just scratching the surface of understanding all of this.
We are, and that's the beauty of science, the constant exploration and discovery.
Exactly. So thank you, everyone, for joining us for this deep dive.
Always a pleasure.
And keep looking up at the stars and keep wondering.
Because the universe is full of mysteries waiting to be uncovered.
Absolutely.
And who knows what incredible discoveries await us in the future.
All right. We'll see you next time.
See you then.